In the previous lecture, we introduced Einstein's view of the universe, a universe in which matter tells spacetime how to curve and curved spacetime tells matter how to move, giving us a radically different view of gravity that is nonetheless experimentally confirmed. We're now going to turn to the consequences of what it means to live in a curved space. Newton viewed space as flat and static, neither expanding nor contracting. A ladybug crawling across a flat plane can travel in a straight line at a constant speed in any direction. No matter which direction the ladybug chooses to walk, there is nothing about the structure of the space the ladybug is walking on that could change or alter its path in any way from the straight line path it set itself upon. Einstein, on the other hand, viewed space as curved and wavy, and furthermore, space can expand or contract. A ladybug crawling across a rumpled rubber sheet, trying to walk in a straight line, would follow a zigzag path that matches the curviness of the surface. Furthermore, which direction the ladybug walked in may affect what its path is going to be. If I look at a ladybug moving through this space, the shape of the space impresses itself upon the motion the ladybug takes. Even if the ladybug is trying its best to walk in a straight line, the definition of straight line changes a great deal when we go into a curved spacetime. It changes even more if that spacetime is allowed to stretch or shrink while the ladybug is in motion. All of these things in a curved, dynamic universe will have observational consequences. Because we are used to perceiving the world in three dimensions, the world of breadth, depth, and height, trying to visualize four-dimensional curved spacetime is extremely challenging for us humans. We often resort to using two-dimensional analogies to illustrate the basic ideas. For example, it's very common to represent curved spacetime around a massive object by imagining a space as a two-dimensional rubber sheet into which I place masses. The masses then cause the sheet to distort and bend, and we get something referred to mathematically as an embedding diagram. We can visualize the curved space around a mass. Here might be, for example, the curved space around the sun. These embedding diagrams, while they look slightly simple to the eye, are actually mathematically more abstract. I've suppressed two of the four dimensions of spacetime, one of the space dimensions and one of the time dimensions. Furthermore, all of the other two dimensions of space are confined just to the sheet, and the distortion of the sheet into what appears to be a third dimension isn't the third dimension of space, it's just a mathematically made-up embedding dimension. It's pretty abstract. And in many ways, these analogies, while they're often useful for helping us visualize what's going on, can also be very misleading. We can only take these analogies so far. If we want to deal with the universe as it really is, we're going to have to deal with four-dimensional space in all of its gory detail. And in practice, that's going to require some extremely complex mathematics. It's some of the most complex mathematics that I ever encountered during my time as an undergraduate and graduate studying general relativity. The little piece I've shown over on the right, that's one of the simpler bits. Let's move on. Numerically, we can also do these modeling in computers, but there the challenges are no less severe. For example, accurately modeling a curved two-dimensional surface still requires a great deal of intensive computation. The world of computer graphics that's given us so many wonderful entertainments like the movies from Pixar require an enormous amount of computation. And what they are doing at their basis is trying to render a two-dimensional surface in a computer. For example, here's an attempt to render a human hand. We can break the human hand's surface, which is a smooth and continuous surface, down into a series of interlocking triangles joined at their vertices. On the right-hand side, we see a model of the human hand using only 500 vertices. It's pretty crude. Looks kind of like what you would expect for the rendering in a really cheap video game. If I go up a factor of 10 and go to 5,000 vertices, it's looking better, but it's still somewhat artificial. Another factor of 5 to 25,000 vertices, and I'm doing pretty good, and then I do the math and realize, yeah, but that's just the hand. You can get an idea of how much computation is involved, by the number of vertices increasing gives you a smoother representation of the surface, but even there, the level of detail is eventually sacrificed by having to make a choice of the number of vertices. How good is good enough sets the limitation on what kind of simulation you can compute. And this is only in 2 dimensions. We're trying to render the picture of a human hand onto a flat screen. Now imagine what it would be like trying to do a high-precision 4-dimensional computation. It remains one of the most difficult computational problems in all of physics. However, we don't have to go to the full 4-dimensional gory detail, either the mathematics or even in the numerical computation, to be able to make a lot of progress in understanding the consequences of general relativity for our observations of the universe. Under most circumstances, Newtonian gravity is a good enough approximation and is computationally a great deal simpler to deal with. Why is this the case? In large measure, it's because general relativity really begins to matter only when you're in the regime of very strong gravity. For example, if I'm doing a general relativistic calculation in the solar system, I really only need to worry when I'm close to the masses that I'm interested in. For example, if I'm sending a spacecraft out to Pluto, like the New Horizons spacecraft that flew by Pluto in July of 2015, I don't need to use the full formalism of general relativity to compute its trajectory and successfully navigate it to its flyby of the Pluto system. I can get away with using the Newtonian approximation to gravity because for most of the trajectory of the New Horizons spacecraft, its trajectory is well described as in the weak gravity regime, and in that regime, Newtonian gravity is a very good approximation to general relativity. If, on the other hand, I was in a strong gravity regime, for example, describing the motion of the planet Mercury, which gets very close to the Sun, I could no longer use a simple Newtonian approximation, because the Newtonian approximation, as we saw in the previous lecture, incorrectly describes the motion of Mercury. It's only when I bring to bear the full power of general relativity that I correctly describe, for example, the precession of the perihelion of Mercury's orbit. That extra little bit makes the difference. As a consequence, while I've introduced a lot of the ideas of general relativity, we need to understand that they're still there and they still play a role, but I can often use computational approximations even on cosmological scales that makes our approach much more tractable and allows me to make progress while the computation technology and our mathematics catches up. To understand the observational consequences of living in a curved space, we can get at it by introducing an idea called the cosmological principle. The cosmological principle states that on large scales, the universe is homogeneous and isotropic. Let's break this down. Large scales means, in practice, on scales larger than the scale of superclusters, approximately 100 megaparsecs. This is scales which are larger, for example, than the sizes of the filaments and voids that we see in the nearby universe, as embodied, for example, in this Sloan Digital Sky Survey map of the nearby volume of the universe. The scale of this map is much larger than 100 megaparsecs, and we are in the scale where we are now able to talk about cosmological large scales. Homogeneous means the same in all places. Isotropic means the same in all directions. Now, by same, bear in mind, I do not mean identical. It's not the same to say that if I go everywhere in the universe, I see exactly the same galaxies with the same colors and the same properties. Just like if you go into a large crowd of people that may be all evenly, homogeneously distributed across the field, you're not going to see exactly the same person unless you wandered into a weird place full of clones. When I talk about homogeneous being same in all places, or isotropic being the same in all directions, these are statistical statements. These are statements about, for example, the number and distribution of galaxies on 100 megaparsec scales, or it might be a statement about the count of the number of galaxies as I look out along a sightline that extends out to and beyond 100 megaparsecs. Our statements about homogeneity and isotropy are purely statistical statements, but for those statistics to work, I have to get onto sufficiently large scales. How large? Scales of 100 megaparsecs. Homogeneity and isotropy hard to say. Homogeneity and isotropy are different. They're very different, and it's important to understand the distinction. Here's a simple analogy. Imagine a target. I'm going to take a look at the target and try to talk about what its properties are with regards to homogeneity and isotropy. This target is isotropic around the central point in the sense that as I look out from in any direction standing in the middle of the target, I see the same variation in pattern from yellow to red, blue, white, then black. It doesn't matter which way I look, I see the same basic pattern. However, if I was to be standing at a different point and look out, for example, if I was standing over here on the blue stripe, then my statement about isotropy would no longer be true. For the target, isotropy is a very restricted idea. The target is also not homogeneous. By homogeneous means, if I look at the target only within a confined circle, here shown by the two blue circles, if I look in the circle on the left, the universe is a red stripe with a little bit of yellow and blue, whereas in the right-hand circle, the universe is black with a little bit of white on either side of it. These two views in these two places do not look the same. Therefore, this target is isotropic only about its center, and it's not homogeneous anywhere, provided I'm looking on scales of order the size of a stripe. Turning instead to this stripe pattern, an alternating pattern of red and white stripes. This pattern is homogeneous provided that the scale of the circle that I'm looking in is bigger than the width of a stripe. For example, by drawing these two fairly large blue circles here, blue circles larger than the scale of the width of one of the stripes, I see around me an alternating white-red pattern with a very characteristic scale for the width of the stripes. If I was looking on a small scale, I would only see a white pattern or a red pattern. I would not be sensible of the repeating pattern. Similarly over here, I'm looking at it slightly differently, but nonetheless, because my circle is larger than the distance between two of the stripes, as a consequence, I can still discern the white-red alternating pattern and the basic scale of their width, so that my view of this striped pattern is homogeneous provided I pick a scale for the size of the circle that I'm using to sample that surface that is larger than the largest characteristic scale that I see in the width in the structure here, the width. It is not, however, isotropic. If I look along the direction and up, I would see an alternating pattern along that direction of red, white. But if I looked along the stripe, it would only look white. The pattern on the right is homogeneous on sufficiently large scales, but it is not isotropic on any scale. This distinction between homogeneity and isotropy is very important when we now turn to asking what are the structure of the universe on large scales. On small scales, the universe is clearly not very homogeneous. Look around you. On scales of kilometers, the world looks very different depending upon where you're standing on it, whether you're in Ohio or Japan or at the Antarctic or out in the middle of the Pacific Ocean. The world looks different on the relatively constrained scales of a human being. Even on the scales of the solar system, things are not homogeneous. I look out around me in the solar system, I see planets, I see asteroids, but I move half a parsec in any direction out into deep interstellar space, I don't see anything around me except a little bit of interstellar gas. Or I might go 100 parsecs away and within the circle the size of the solar system. I might have a star or I might have nothing. The universe is not homogeneous on 100 parsec scales. And it goes on to even greater distances. If I go out to scales of 50 megaparsecs, for example, so I take a section here of the Sloan map of the universe, and I draw a circle of diameter 50 megaparsecs. If I plop that circle down here, I might find myself with a gigantic supercluster of galaxies. Each one of these black dots is an individual galaxy or group of galaxies. There, I see a supercluster. But if I pick another 50 megaparsec bit, one not very far away, well, I might see a filament and a couple of voids in here, but this place on the right looks very different than the place on the left. On 50 parsec scales, the universe is not very homogeneous. It's only when I get out to large scales, and that scale begins to pick up at about 100 megaparsecs, that I can begin to make statistical statements about different regions in the universe. For example, I'm out here at 100 megaparsecs, and I see voids, I see filaments and walls. I pick another 100 megaparsec region, and I see voids and filaments and walls. If I stare at these two patterns, they do look different. They have a different detailed pattern. But statistically speaking, I have the same density of galaxies, the same distribution of walls and voids within each of these 100 megaparsec across volumes. As I go to larger and larger scales and sample more and more of the universe, statistically things do not begin to change. This illustrates the idea that our universe is in fact homogeneous, but it is homogeneous on very large scales. I have to get out beyond the scale of the largest organized matter in the universe, the voids and filaments and walls, before that homogeneity becomes manifest. It's all a question of scale. Similarly for isotropy. The universe is statistically isotropic on 100 megaparsec scales along any line of sight. The sun is down at the vertex of this cone looking out into the universe. If I chose various different sight lines, provided that I count, for example, the number of galaxies, as long as the number of galaxies I count is counted out to distances of 100 megaparsecs or more, then on average I will see the same number of galaxies along this line of sight as along the next line of sight as along the next line of sight, provided that I'm counting along a distance of 100 megaparsecs or more. If I counted over a short distance, I might find a lot of galaxies on this sight line, but on this sight line, I would find myself in a void. I would get very different answers. So again, this idea of homogeneity and isotropy only holds on the very largest scales, the scales of the largest superclusters of galaxies, of the voids and filaments and walls.